Physics with Nunez.
Hi, AP Physics. Today I just wanted to take a moment to talk about rotational inertia and go a little bit more in depth in the concept. What you should have out during this brief video is the AP Physics Lesson 1.1 handout that I posted on Monday. Your reference sheet would be helpful, and our objective today is to understand rotational inertia. So like Mr. Tarek pointed out in his video, rotational inertia is a property of an object or system that depends on two things. It depends on how much mass it has, but it also depends on where that mass is relative to how the object is rotating, which sounds a little bit complicated, and it kind of is, but I'm hoping today I can alleviate some of that confusion. So rotational inertia is going to be given by the variable I, and it's always going to have the units kilogram meters times meters squared, which makes sense given that the equation is just mass times distance squared. Now, the nice thing is you are almost never going to need to use this equation on the AP exam. In fact, as it's written, it's not terribly useful unless your object is very simple. As you get into more advanced sciences and physics, you will end up using this equation more with calculus, where it is much more useful, but you do need to have an understanding of how this equation works. And so what it essentially tells us is that, let's say I had some object, let's say it was a square plate, and I had a tiny mass sitting on 4 different points on that square plate. If I wanted to figure out the rotational inertia, I would need to apply the equation above to each of these masses relative to the center of my square. So in this case, let's say my square was rotating around its center point. So this would be my center point. I would need to know this R, this R, this R, and this R. And I would essentially set it up by doing m times r squared plus m times r squared plus m times r squared plus m times r squared for each of the 4 masses. And so what I would get is I is equal to 4mr squared. And so, like I said, this is only really useful in small, simple objects. If we had something a little bit more complicated, where our object was this big curvy shape, and let's say we were going to rotate it around this point right here, and I gave you an object of mass big M and an object of mass little m, you would have to measure this distance, and then apply the equation that way. You would also want to take into account the mass of the actual object. Whoops. And because it's curved, it gets to be a little bit more tricky. So I say all of this just so you know that you're not going to have to use this equation this often. Now, what I have done is I set up a little mini demonstration to show you how this shows up in the real world. So we're going to cut to that demonstration now. Okay, so what I've set up is 2 objects with different rotational inertias. So you can see in this object, all of the masses are really close to the center of mass, this pivot right here. And in this one, all of the masses are sitting far away from the center of mass, which is the pivot right here. So we would say that because r is small, this has a small rotational inertia. And because r is big, the distance between the masses and the center of mass, because that r is big, this one has a bigger rotational inertia. And what we're going to see is which one, when rolling, goes down this ramp first. Okay, so I've listed the help of Miss Lawhon, who's going to release these 2 objects. So again, this one has a small rotational inertia because the mass is really close to the center of mass. And this one has a large rotational inertia because the mass is far from the center of mass. And we're going to see what happens as she rolls them down the ramp. 3, 2, 1, go. Okay, hopefully after seeing those 2 objects roll down the ramp, you were able to see that the object with a smaller rotational inertia hit the bottom first. Basically, when all of the masses, those four little masses, were really close to where it was rotating, it was able to move faster. If we remember all the way back from Unit 1, inertia is an object's tendency to resist motion. So rotational inertia is an object's tendency to resist rotating. Basically, the more inertia you have, the less you want to rotate. So when those masses were further away, it didn't want to rotate as much, so it moved down the ramp slower than the one that had the masses closer. Therefore, it had less rotational inertia. It was more willing to roll, and so it could roll faster. If we apply that idea to this problem, we see that three flat objects, one is called a circular ring, where there is no mass in the middle, one is a circular disc, where there is mass in the middle, and one is a square loop, where there's no mass in the middle and its shape is a square, all with equal distances from n to n. They all have the same mass m, so they're all big M, and they all have the same diameter. The question is, let's rank the moment of inertia. So let's really quickly just talk about this. Rotational inertia goes by another name, as with a lot of things in physics. Rotational inertia is also known as the moment of inertia. If you pursue a career in civil engineering, which is what I did, moment of inertia and moments are very important because they talk about how things rotate, like bridges and buildings and stuff like that. So I just want to be sure you know what moment of inertia is as well. But the idea is essentially the same. What we need to think about is we need to think about both the mass and how far that mass is from where it's rotating. So if we look at object A, we see that all of the mass is at the edge of the circle. And so all of the mass is a distance of 1r away from the center. The square loop, although this side is 2r, if we were to think about where this mass is from the center, it's actually not equal to 1r because this is a triangle. This would be 1r, and this would be 1r. And so if we use Pythagorean's theorem, this would actually be, and you're like, oh my God, Pythagorean theorem, really? This would actually be the square root of r squared plus r squared, which is slightly greater than 1r. So this actually means that there's more mass further from where it's rotating. So that r value in our equation, mr squared, is actually high for this right here, versus in A, where all of the mass was only 1r away from the center. So the square loop has more rotational inertia than the circular ring. But what about the circular disc? Remember, the total masses of all of these objects are the same. So although the ring and the disk have the same amount of mass, the ring's mass is all 1r away from the center. But on the circular disk, some of the mass is actually really close to the center. Some of it's just a little bit further, and some of it's just a little bit further. And actually very little of it is 1r away from the center, or from where it's rotating. So all objects have the same m. So in order to rank them, all we are considering is the distance away from the center. And what we said was C, the square, has the most mass the furthest from where it's rotating. The ring has everything 1r away from where it's rotating. And the disk has some of its mass that's, the ring is A. The disk actually has some of its mass that's closer to where it's rotating, so that r is very small, and so it has the least moment of inertia. There's some cool YouTube videos that I'll link to you guys that show all of these different types of objects rolling if you don't believe me. But the big thing to know is to internalize. You have to consider both the total mass and how far that mass is from where it's rotating. Hopefully this helps as you complete your exit ticket, and I will talk to you guys soon.